Find that function. Let f be the function from the real numbers to the real numbers be a continuous function such that f of x plus y is equal to f of x plus f of y for all real numbers x and y. This is what's known as a functional equation, and they're very popular in the Math Olympiad. So what's our first approach to trying to find the function that they're alluding to here? Well, first we're going to want to try and pick a few nice values for x and y. And what do I mean by nice values? Well, let's choose 0 for both x and y and see what happens. This functional equation reduces down to f of 0 is equal to 0. So we've found at least one value of our function. Let's see what else we can find. Let x and y be x comma x, meaning let y equal x. And that leads us to the formula f of 2x is equal to 2 times f of x. So we're going to explore if this kind of a pattern would hold if we repeat the process and let y equal 2x. And we see that from that and the past relation we get f of 3x equals 3 times f of x. So now we're going to generalize this for n number of iterations. In other words, let's let y equal the sum of many x's that are identical to the first x, so that we get the functional equation f of n times x is equal to n times f of x. Now this is going to be very helpful in the next step. Since f of is a continuous function, we want to explore not only natural numbers, but perhaps let's try some rational numbers as well. So the next step will be as follows. Using this functional equation, let's let x be the rational number 1 over m, where m is not 0. And that would also mean that m times x is equal to 1. So from the functional equation, f of n times 1 over m, or f of n over m, is equal to n times f of 1 over m. Now we can play around with this a little bit. That f of 1 over m, okay, we can look at that a little bit further. So let's look at f of m times x as f of 1, and let's let f of 1 be some constant we'll call c. Then since f of mx would be the same as m times f of x from the relation, this gives us that f of 1 is equal to m times f of 1 over m, and that's going to be equal to c. And so therefore f of 1 over m will be equal to c over m. So now we can replace that back into equation 5. And when we do that, we're going to be able to deduce that for any rational number, we're going to have a certain type of outcome. Alright, so pause the video now if you have to look this over. Okay, so now applying that last step, that gives us that f of n over m is the same as c times n over m. So that means that if we let n over m be any rational function which will generalize to the letter q, and the big Q is the set of all rational numbers, for any rational number q, when we plug it into this function, we receive the output of c times q, or c times that rational number. So again, because f is continuous, this gives us a general form for what the equation for the function is going to be. Any input that was a natural number or any input that is a rational number both came out as a constant times that number. So we can generalize the formula that if f of x is continuous, for all real numbers x, f of x is equal to c times x. And since c was the value of f of 1, the set of all functions that satisfies this functional equation is f of x is equal to f of 1 times x. A nice Cauchy style problem. The next one is a little bit more involved. The functional equation has some more moving pieces. So I began with this one to give you a taste of just what functional equations and solving them can look like, but some of them can be very different. The next one, find all functions f from the real numbers to the real numbers such that f of 1 plus x times y minus f of x plus y is equal to f of x times f of y for all real numbers x and y. And we also have the given condition that f of negative 1 is not equal to 0. That little tidbit of information will help us narrow down the exact form of the function we're trying to find here. This is also an Olympiad problem. So trying out some nice values as we did in the last problem, x equals 0, y equals 0, we get f of 1 is equal to f of 0 times f of 0 plus 1. And if we let xy equal 1, 1, we get the relation that f of 1 is equal to 0. So we now have a value for our function. And we can put these two things together to deduce that if this were the case, f of 0 is equal to 0, or f of 0 is equal to negative 1. Now furthermore, if we just let the point be x comma 0, let x be free and y equal to 0, we get down to the condition where f of x would have to be 0, or f of 0 has to be equal to negative 1. And if f of x would equal to 0, then we couldn't have the condition that f of negative 1 is not equal to 0. So therefore f of x is not equal to 0 all the time. And therefore f of 0 is equal to negative 1. So now we have two values for f. And here, one more that we can get is if we let x equal negative 1 and y equal 2, we can get the value for f of 2 to be equal to 1. So what I'm doing here is trying to build a table of values, and when I do this, I can see what looks to be a linear type function, a linear trend. So we're going to set up a linear function ax plus b and use some of the values in there to deduce that f of x would equal x minus 1, a linear function. And so the last part to that would be maybe to show that this particular linear function satisfies our functional equation. Okay, but take a moment to pause the video here just to see how we deduced that linear function from the table of values. Here we see the functional equation is satisfied by the function f of x equals x minus 1, and therefore we've found our mystery function. This one didn't go exactly as the last one did, but you can see starting it off, we really wanted to try a few nice values for x and y and see if we can generate some idea about the trend that this function is following. And perhaps from your knowledge of functions, you can then start to predict what to do from there. So there you have it, another Olympiad level problem. But wait, there's more. We have just one more to take a look at, and it involves polynomials. Find all polynomials p of x with real coefficients such that for all real numbers a, b, and c, where a times b plus b times c plus a times c is equal to 0, we have the following functional relation. P of a minus b plus p of b minus c plus p of c minus a is equal to 2 times p of a plus b plus c. Now, something to note about this particular functional equation, as with many, is that it is a linear equation. What that means is that we can multiply it by a constant, and that will also satisfy the functional equation, as well as if we have two solutions, p and q, those two polynomials can be added together and a linear combination will also satisfy the functional equation. So those two pieces together will help us stitch together what the polynomial that we're looking for will be. So keep this in the back of your mind and let's get to it. We are going to start with the most general case of a polynomial. That is what one might call a power function, x to the nth power. And from there, we'll try to work our way out to see what kind of other pieces will be involved. So let's suppose that p of x is x to the nth power, where n is a number greater than or equal to 0. and n is a natural number if this is going to be a polynomial. So now, observe that if AB plus BC plus AC equals 0, then that also means that if I wrote down the fractions 1 over A plus 1 over B plus 1 over C, that too would have to equal 0. And you can check this for yourself. So from that relation, it helps us generate a few solutions for A, B, and C, namely 2, 2, negative 1, or 3, 6, negative 2. Now with a few solutions found, and you can verify that they are solutions, we can play around with that to see what sort of values this polynomial might give us. What you see here is that we find out that no matter what we do by inputting the values of the first solution, we get negative 3 to the nth power is equal to positive 3 to the nth power. This tells us that n, the exponent, is an even number. So that helps us out in the beginning to generate an idea of what p of x is going to look like. So we have x to an nth power where n is an even number. So now we have to narrow down perhaps what even numbers are possible and which ones are not. You see, we have to make sure that we satisfy the functional equation. Is n equal to 0? If n were equal to 0, x to the 0 power would always equal to 1, and our functional equation would lead 1 plus 1 plus 1 is equal to 2 times 1, or 3 equals 2, which is not true. So n must be greater than 0. So it's an even number greater than 0, and using the other solution that we found, 3, 6, negative 2, we can generate another equation which must be satisfied here. 3 to the nth power plus 5 to the nth power plus 8 to the nth power must be equal to 2 times 7 to the nth power. And this was generated by working through the solutions and then using the fact that n was an even number to get rid of those negative parts in our functional equation. So this is the equation that we have to make sure satisfies for the n values that'll work. And if you take a close look at this equation, you'll notice that if n gets sufficiently large, then that 8 to the nth power would dominate the left-hand side of this equation, and therefore it would overtake any 7 to the nth power at some point. So we have to figure out at what point it takes over. And if we look at the inequality between 8 to the n and 2 times 7 to the n, right around n equals 6 is when we get a switch of inequality, and it'll continue to be that for forever. So now we would have to prove that that would happen forever through induction, meaning that to prove that for n greater than or equal to 6, that inequality holds true, and therefore the equality up there would not be able to hold true. Okay, so the claim here is that 2 times 7 to the nth power is less than 8 to the n for all n greater than or equal to 6. And I can reduce this down to a more simpler inequality. 7 to the n is less than 2 to the 3n minus 1 power for all n greater than or equal to 6. From our table of values, the first case holds true for n equals 6, and we assume that for some k greater than 6, that this inequality does in fact hold true. And using that relationship, that assumed truth, we can then show that the k plus 1 step would also hold true here. And so this is just a proof by induction here, and we in fact get down to the value that in fact it will always hold this inequality for n greater than or equal to 6. Therefore, the functional equation, the equality, will not hold for anything greater than n equals greater than or equal to 6. So the only even values that would be possible for n to be would be the value of 2 and 4. So now we just have to check that those in fact work. And if we plug in n equals 2 into the functional equation that we generated with the solution, we see that it is in fact true. So p of x is equal to x squared is in fact a solution. As well as a constant multiple of that would also be considered a solution, and we'll stitch that together in a moment. You can go ahead and check for the functional equation if p of x is equal to x to the nth power, that it is in fact satisfying both these equations, the one for the n equals 2 case and the one for the n equals 4 case. And with a little bit of algebra, you could, in fact, verify that to be true. So let's consider p of x to be x squared, q of x to be x to the 4th, because both 2 and 4 work as powers, and any linear combination of this would be alpha x squared plus beta x to the 4th. That would be the polynomials, the set of polynomials, all polynomials with real coefficients that satisfy this particular functional equation for some constants alpha and beta. Well, there you have it, a little taste of functional equation fun. I hope you enjoyed it. Please hit that like, subscribe, and notification bell for more videos, and stay tuned for the next one. Thanks for watching.